So at this point, we've talked a bunch about magnetic flux and how you could think of it as the amount of magnetic field enclosed in a conductor. We've also talked about Faraday's law, that the speed at which you change the flux is directly proportional to the EMF induced. And you can use that to find currents that flow through the conductors. There's one thing we haven't talked about, though, and that's this negative sign. And that's what the point of this video is about. The negative sign is what we know as Lenz's law. And it basically says that if you change the amount of flux enclosed in a coil, nature's going to try to fight you on that. It's going to try to create a current such that the change you make is counteracted. So if I had more inward flux going all of a sudden, a current would induce in this coil to try to give me some outward flux to cancel out the new inward flux. Let's take a look at what this looks like practically.
I wanted to show you guys one of my favorite demonstrations, which was put together by the Arbor Scientific Company. It's a piece of pipe that's open so you can kind of see what's going on. And we've got these two kind of steel slugs. And one of them, as I drop, kind of looks exactly like you'd expect. It moves very, very fast. And that's just like it would fall in free fall. The other one, though, does something really unexpected. It takes a really long time to fall. So since this is the magnetism unit, you could probably guess that the second one was a magnet. But that's a kind of odd thing, because copper is not magnetic. And neither of these is actually going to stick to the copper on the outside. So what's going on? This is an example of the beautiful symmetry between electricity and magnetism, and Ørsted's law that currents can cause magnetic fields, and Faraday's law that moving magnetic fields can cause currents.
So I've tried to draw that here. The magnetic field lines of this magnet are going into the south. So basically inside the magnet they're running up. And as the magnet slides through the tube is a conductor. And that's changing the flux inside the conductor, and that's going to induce an EMF and a current. Well, which way should that current travel? In this case, it's traveling clockwise because such a current would produce the opposite magnetic field from that of the magnet. And that means that as this thing falls, the flux change produced by the fall is opposed by this current that showed up. So you've got two magnetic fields opposing each other, and these essentially act like two magnets in repulsion, and that's what slows the falling magnet down. So I like to call Lenz's law, if you try to change nature, it will fight you. But more specifically, it's that if you change the magnetic flux in a conductor, it'll induce an EMF and a current that essentially opposes that change. Strangely enough, this principle is used in the functioning of an electric guitar. If you look at an electric guitar, there's these things called pickups. And what you've got are magnets, which have their own magnetic field, and then you have a coil of wire running perpendicular to them. So I've drawn that here. Here's our coil, here's our magnet. And we also have the string running over it, which is made of steel.
You pluck the guitar string, you make it move up and down, and that's what's going to make your note. And we'll learn in our wave unit about what makes the different vibrations so that things sound differently. But the key thing is this magnet actually slightly magnetized the steel string. It caused atoms in the string to line up with its magnetic field, which I've drawn in green. So when the string goes up and down, now we have a small moving magnet. Well, what does that cause? A current in the coil of wire. And then that's what gets fed to the amplifier so that you can hear what's going on with the guitar. So I just think that's a beautiful symmetry. Currents cause magnetism, magnetism causes currents.
And I hope after this video you feel like you've got a better understanding of both how big the induced EMF and therefore current is. Depends on how fast magnetic flux changes, but now also its direction. The direction of the current will be to oppose any changes in magnetic flux caused by the motion.